Hello everyone. In today's class we'll be doing P-block, and as you can see in P-block we'll be doing the 17th group. These 17th group elements, they are also known as halogens. We'll be studying about their physical properties like their atomic radii, their electronegativity, their ionization enthalpy, their electron gain enthalpy, their oxidation state, their elemental state, and after that we'll be studying about their chemical properties also. Well, chemical properties, they include reaction with hydrogen, reaction with oxygen, and reaction with halogens. We'll see what are all these elements which are present in 17th group. Well, the elements are fluorine, chlorine, bromine, iodine, and astatine. We'll not study about astatine because it's radioactive. Very commonly, these 17 group elements, they are known as halogens. First, we'll see their atomic radii. Well, as far their atomic radii is concerned, they are smallest in their respective periods. Dear students, I'm not writing everything over here. I'm explaining you something, like I'm telling you that their atomic radii is smallest. So you have to keep that in your mind, or if you want to write it down somewhere, you can write it. Their atomic radii is smallest in their respective periods, because after them comes noble gases which have got slightly larger atomic radii due to prominent interelectronic repulsion. The second physical property of 17th group elements which we are talking about is electronegativity. Well, halogens, they are the most electronegative elements in their periods, and on moving down the group, their electronegativity decreases. Next comes their ionization enthalpy. They does not have a tendency of getting ionized easily. So we have a very high positive value of ionization enthalpy. We need to apply a lot energy in order to take out an electron from them. Next, fourth, is their oxidation state. Well, as far oxidation state is concerned, we'll see that in detail. Like here I'm again writing the elements fluorine, chlorine, bromine, and iodine. All these 17th group elements, they have 2 electrons in their valence s subshell. They have 5 electrons in their valence p subshell. That means their general electronic configuration is ns2 and p5. Now, what happens? They have a tendency of prominently withdrawing an electron from any element and get stable. Since they are the most electronegative elements in their respective periods, so they have a common tendency of exhibiting -1 oxidation state. We know one thing, that fluorine is the most electronegative element of the periodic table. So fluorine can exhibit only one oxidation state, that is -1. Well, as far rest of the elements are concerned, apart from fluorine, the rest of the elements, then they are not only slightly less electronegative, but they also have a vacant d subshell in their valence shell. So these elements, they can easily lose this unpaired electron. They can share this unpaired electron to some other element like oxygen, which is second most electronegative. And in that bond, they can easily lose electron to oxygen. That's why they have a tendency of exhibiting +1 oxidation state. So chlorine, bromine, and iodine can exhibit +1 oxidation state, but fluorine exhibits only -1 oxidation state. In chlorine, bromine, and iodine, one more possibility is there, that one of the electron from the p subshell can get unpaired. It can jump to the d subshell. When it will jump to the d subshell, you will have 3 unpaired electrons. So they can exhibit an oxidation state of +3 also. Well, if another electron from the P, it also jumps to the D, you will get 5 unpaired electrons. So they can exhibit an oxidation state of +5 also. And in elements like bromine and iodine, this S electron also jumps to the D. So they can very commonly exhibit an oxidation state of +7. Chlorine exhibits +7 oxidation state but to a lesser extent due to inert pair effect. Bromine and iodine have got a tendency of exhibiting +7 oxidation state quite commonly. I can give you an example of a compound like IF7. You have already done this. In this compound, iodine is exhibiting an oxidation state of +7. So all of them, they can exhibit -1 oxidation state. Fluorine can exhibit only -1. Rest of the halogens apart from -1 can exhibit an oxidation state of +1, +3, +5 and +7. After that, we'll see their elemental state. Well, if I talk about elemental state, perhaps halogens is the only group in which we see all the three elemental states. That is gas, liquid and solid. In rest of the groups, we don't see this. Like if I talk about boron, in boron group, all the elements they are in the solid state. If I talk about carbon, there again. If I talk about say nitrogen, there nitrogen is a gas, rest all elements they are in the solid state. If I talk about oxygen, then oxygen is the gas, rest all elements they are in the solid state. So you can see maximum of two states. If we talk about the first or second group elements, all the elements they are in the solid state. This is the only group where you got solid, liquid and gas, all the three elemental state. So if we see fluorine and chlorine, if we talk about fluorine and chlorine, they exist. Fluorine and chlorine, they exist in the gaseous state. And if I talk about bromine, it exists in the liquid state. If I talk about iodine, it exists in the solid state. So all the three states we can see in halogens, that is solid, liquid and gas. So elemental state, all three elemental state we see. And why this gradation is there? Because as we are moving down the group from fluorine to chlorine, chlorine to bromine and bromine to iodine, the molecular mass is increasing. So the van der Waals forces there also increases. Hence the state is changing from gas to liquid and liquid to solid. Now we'll talk about their electron gain enthalpy. Electron gain enthalpy. All halogens, they have a higher negative value of electron gain enthalpy. That is, when you add an electron into them, they are like this. If you add an electron into them, they will get converted to a halide ion, and along with that, they will give large amount of energy. You will get large amount of energy. So they got a higher negative value. Now I want to tell you one thing here, that as for the electron gain enthalpy, the negative value of electron gain enthalpy is concerned, it is directly proportional to the electron negativity. All halogens, they are highly electronegative. So they have a tendency of attracting electron and losing large amount of energy as electron gain enthalpy. Now in these elements, if we see, fluorine is the most electronegative element. So we expect that the electron gain enthalpy of fluorine will be most negative, whereas it is not like that. The electron gain enthalpy of chlorine is more negative than fluorine. We'll see why it happens, and this is a quite prominent question which is asked many a time, that although fluorine is more electronegative negative than chlorine. Why? Electron gain enthalpy of chlorine is more negative. Well, the answer to this question is that fluorine has got a smaller atomic radii. Since fluorine has got a smaller atomic radii, it has got a denser electronic cloud. Now, when it has got a denser electronic cloud, if you add an electron to fluorine atom, no doubt the nucleus will attract that incoming electron, but the electronic cloud, which is dense, will repel that incoming electron. So, as a result of that, lesser amount of energy is given out. We know one thing, that wherever there is high attraction, there is always lowering of energy. And so, large amount of energy is given out. So, had there been a prominent attraction between the nucleus and the incoming electron, large amount of energy would have been given out. And no doubt it is like that in fluorine. Although the nucleus is attracting the incoming electron to a very large extent, but there is also a prominent repulsion between the incoming electron and the electronic cloud. So due to that repulsion, lesser amount of energy is given out. Chlorine does not have such a denser electronic cloud. So in chlorine, when we add an electron, the nucleus simply attracts it. No doubt the attraction is not as strong as in case of fluorine, but there is no repulsion between the incoming electron and the electronic cloud. So since there is no repulsion, the energy which is given out is more than that of fluorine. So although fluorine is more electronegative, but electron gain enthalpy of chlorine is more negative than fluorine. After this, here we have seen electron gain enthalpy, we have seen elemental state. We'll talk about their bond dissociation enthalpy. This is the last physical property we'll be doing. That is bond dissociation enthalpy. What does bond dissociation enthalpy means? It is the amount of energy that is required to break this bond between two halogens. Like you got a bond between fluorine, fluorine, or chlorine, chlorine, or iodine, iodine. Now we know that halogens, they have got the smallest atomic radii. Now since they have smallest atomic radii, that means the bond between two halogens is quite small. Smaller the bond, stronger it is. So we need more energy to break it. That's why halogens have got a higher bond dissociation enthalpy. Among these halogens, we expect fluorine to have the highest bond dissociation enthalpy because fluorine is smallest in radii. So since fluorine is smallest in radii, we have a perception that bond between fluorine and fluorine will be smallest. And so we need more amount of energy to break this bond, whereas it is not like that. Although fluorine has got the smallest atomic radii, but its bond dissociation enthalpy is lesser. Again, this is an anomalous question, anomalous behavior which we are seeing, and that's why it becomes important. In P block, anything which is away from the regular trend becomes important. So the regular trend, according to the regular trend, the bond dissociation of enthalpy of fluorine should have been the highest, whereas it is not like that. It is lesser than chlorine. Why it is lesser than chlorine? Why the bond dissociation enthalpy of chlorine is more than that of fluorine, although chlorine is larger as compared to fluorine? Because fluorine has got a denser electronic cloud. Now since fluorine has got a denser electronic cloud, I am explaining it to you. Now suppose these are the two fluorine atoms I have got. They have got a denser electronic cloud. Although they are smallest, I am expecting them to come very close to each other. But since the electronic cloud is denser, these two fluorine, they will experience some repulsion. So they will not come so close to each other as we were expecting. According to their atomic radii, they should have come very close to each other. But since they have got a denser electronic cloud, this electronic cloud repulses each other. And as a result of that, they come a bit close, but not to that extent which we were expecting. So the bond between two fluorine atoms is not as small as we were expecting. And so since it is not as small, so it means it is not as strong. Hence it becomes easier to break this bond. So fluorine has got a lesser bond dissociation enthalpy than chlorine. Fluorine bond dissociation enthalpy is lesser than that of chlorine. This is what you have to remember. And this is all about their physical properties. Now we'll see their chemical properties. chemical properties. As I already told you that when I am talking about chemical properties, I'll be talking about their reaction with hydrogen, reaction with oxygen, and reaction with halogen. So first we'll see their reaction with hydrogen. Well, all 17th group elements, they have a tendency of reacting with hydrogen and forming HX type compound. Like you have HF, HCl, HBr, or HI. So all of them they react with halogens. All of them they react with hydrogen to form HX type compound. Now we'll see the properties of these compounds. First we'll see their boiling point. And kindly pay attention toward this thing because many a time these questions they have been asked. Boiling point. I tell you what type of question you can get on this. In this, the question can be framed like give reason why HF is a liquid while HCl is a gas at room temperature, although the molar mass of HCl is more than that of HF. Give reason why, although the molar mass of HCl is more than that of HF, yet HCl has got a lesser boiling point than HF. So we'll see what's the trend of boiling point and we'll see how it happens. For that I would like to show you a graph. Suppose I am plotting a graph between the boiling point and the molar mass. Here somewhere I have got HF. Here somewhere I have HCl. Then I have HBr. Then I have HI. I can join it like this. You can see as we are moving from HCl to HBr to HI, the molecular mass is increasing, so the van der Waals force is also increasing, and as a result of that, the boiling point will increase. But the question comes to our mind, why the boiling point of HF is higher? It has got the least molecular mass, so its boiling point should be the minimum, but it is unexpectedly higher. It is because unlike HCl, HF has got a prominent intermolecular hydrogen bonding. So if we have a look at a HF molecule, HF molecule is like this. It exists like this. And in all these molecules, F is negative, H is positive. So F is negative, H is positive, F is negative, H is positive, F is negative, H is positive. So it will form hydrogen bond here. Again you'll have hydrogen bond, hydrogen bond, hydrogen bond, likewise. So all these HF molecules, they are attached to each other by prominent intermolecular hydrogen bonding. And due to that, they have got a higher boiling point as compared to HCl. So although their molar mass is lesser, yet their boiling point is higher. After boiling point, next we'll see, second we'll see their acidic character. All 17th group, all compounds of 17th group elements with hydrogen have got an acidic character. Like if I have HX, we know X is always more electronegative than hydrogen. So it has a tendency of attracting the electron toward itself. So X will become negative and H will acquire a positive charge. So very prominently this bond will break and you will get H positive and X negative. So all compound of 17th group element with hydrogen have a tendency of withdrawing electrons from hydrogen, releasing hydrogen as H positive ion, and that's why they are protic acid. Now the question comes to our mind, which among them is most acidic and why? Well, as we move down the group, see all halogens, again I'm drawing this molecule, all halogens, they are so highly electronegative that they can easily withdraw these bonded electron, no matter I am talking about chlorine, bromine or iodine. So all these compounds, they exhibit acidic character. But what happens on moving down the group? On moving down the group, the bond between hydrogen and halogen becomes longer and weaker. So it becomes easier to donate H positive ion. That means if I talk about their acidic character, HCl is less acidic than HBr, and that is less acidic than HI. I am not writing HF because HF is not at all acidic due to prominent intermolecular hydrogen bonding. It has got a prominent intermolecular hydrogen bonding, as you can see here. So it will not donate H positive ion in the free state. So HF is not at all acidic. HCl, HBr and HI are acidic, and on moving down the group, their bond length increases, bond strength decreases, so it becomes easier to donate H positive ion, and therefore the acidic character increases. Next, we'll talk about their reducing character. Reducing character. Well, any element which has a tendency of donating hydrogen is a good reducing agent. So all these halogen, this compound of halogen with hydrogen have a tendency of donating hydrogen. As I have shown you that on moving down the group, bond length increases, it becomes easier to donate hydrogen. That's why the reducing character increases. That means HI is a better reducing agent as compared to HBr. HBr is a better reducing agent as compared to HCl. So reducing character increases on moving down the group. Likewise, the last point in this is thermal stability. We'll see what does thermal stability means. Now suppose I have got a compound like HX. If I heat it, the bond between H and X will break. It will break into H2 and X2. If the compound is thermally stable, this reaction will not occur. As we move down the group, from chlorine to bromine and bromine to iodine, the bond length increases. So the HX bond length increases and bond strength decreases. Hence, it becomes easier to donate hydrogen. So we can say thermal stability decreases. That means HCl is thermodynamically more stable than HBr, and HBr is thermodynamically more stable than HI. So thermal stability decreases on moving down the group because bond length increases, bond can easily break, hydrogen can easily be donated. This is all about their reaction with hydrogen. Next we'll see their reaction with oxygen. So second is reaction with oxygen. The same topic is in 16th group also. There we call it reaction of oxygen with halogens. The same type of compound we'll get. Well, as far fluorine is concerned, fluorine combines, or I'll write all the elements like fluorine, chlorine, bromine and iodine. Fluorine combines with oxygen to form only one compound, that is OF2 type compound. Rest all halogens, they combine with oxygen to form Cl2O, Cl2O3, Cl2O5 and Cl2O7 type compound. Same goes for bromine also. You will have Br2O, Br2O3, Br2O5 and Br2O7. Likewise, I2O, I2O3, I2O5 and I2O7 type compound. The compound of oxygen and fluorine is very correctly known as oxygen difluoride because fluorine is more electronegative. Whereas the compound of rest of the halogens with oxygen is known as their corresponding oxide, like chlorine, dichloromonoxide, dichlorotrioxide, dichloropentoxide and dichloroheptoxide. You can easily see that in these compounds, the halogens, they are exhibiting their +1 oxidation state, +3 oxidation state, +5 oxidation state, and +7 oxidation state. Whenever we talk about compound with oxygen, which are known as oxide, we generally talk about their acidic or basic character. Because oxides of metals, they are always basic, and oxides of non-metals, they are always acidic. Since halogens are non-metals, so their oxides are acidic. We'll see their acidic character. Well, I'll give you that example, means I'll explain that to you. They are also acid by taking example of chlorine. Same goes for bromine and iodine. I'm writing chlorine oxides like Cl2O, Cl2O3, Cl2O5, and Cl2O7. If I react these compounds with water, if I react this compound, this one, I will get 2 moles of HClO. This compound on reaction with water will give me 2 moles of HClO2. This compound on reaction with water will give me 2 moles of HClO3. And this compound on reaction with water will give me 2 moles of HClO4. The first compound is known as Hypo Chlorous acid. Very commonly we call it hypohalous acid. Had it been bromine, hypobromous, hypoiodous, so this is hypochlorous. Then you have chlorous, then you have chloric, and in the last you have perchloric. So hypochlorous, chlorous, chloric, and perchloric acid we get. For any halogen, we can say we have hypohalous, halous, halic, and perhalic. Many a time, a question is asked whereby you have to compare their acidic character, which among them is most acidic. Here I would like to tell you that hypochloric acid, perchloric acid is most acidic. Why it is most acidic? Again, we take in consideration the 2 points which we have already done in organic chemistry, like plus I and minus I effect and the stability of the conjugate base. Well, if I talk about these acids, their structure is like this: HOCl. Here it is HOCl double bond O. Here it is HOCl double bond O, and here you have a single bond. In this case, it is HOCl double bond O, and double bond O. First point, if we talk about the first point, we'll take in consideration the first point, that is minus I effect of oxygen. You know that oxygen is the second most electronegative element. So oxygen has a prominent tendency of withdrawing electrons. So more the number of oxygens, easier will be the withdrawal of electron from hydrogen, and easier will be the donation of H positive ion. So in the first compound, you can see one thing, that this oxygen will withdraw electron, it will become negative, it will donate H positive ion. So here you will get H positive ion and you will get ClO. Well, here I would like to correct it a bit. It's not actually a double bond which I have drawn, it's a single bond. So we'll get ClO negative. In this one, if we talk about the second acid, you have got more number of oxygen. That means more easily electrons will be withdrawn and H positive ion will be donated more easily. And you'll get ClO2 single negative. After that, in the third one, which has got 3 oxygen atoms, the removal of H positive ion will still be easier as compared to the second one. It will be easier one. You'll get this. In the fourth one, where you have got 4 oxygen, it is the easiest one. All 4 oxygen, if we talk about them, they are second most electronegative element. So they can easily withdraw electron from hydrogen and they can easily donate H positive ion. So in perchloric acid, the H positive ion will be donated most easily, and you'll get a conjugate base like this, whereby you have 4 oxygen atoms. You'll have O negative. So, according to the first point, that is minus I effect of oxygen, more the number of oxygen, more will be the electron viscosity, easier will be the donation of H positive ion. So, according to this factor, HClO4 is more acidic than HClO3, that is more acidic than HClO2, and that is more acidic than HClO. So, this is the trend of acidic character of oxo acids of chlorine, according to minus effect. The second factor is the stability of conjugate base formed. Stability of conjugate base formed. Here I would like to tell you one thing, that the acidic character of these oxo acids is directly proportional to the stability of conjugate acids. So their acidic character is directly proportional to the stability of conjugate acids. The stability of conjugate acids is directly proportional to the extent of resonance, and the extent of resonance is directly proportional to the number of oxygen atoms. So in perchlorate ions, in this ion, you'll see there are maximum number of oxygen atoms. That means maximum resonance. Maximum resonance means perchlorate ion is most stable. That's why perchloric acid is most acidic. And as you move from perchloric acid to chlorate to chlorous to hypochlorous, the number of oxygen atoms is decreasing. So the extent of resonance is also decreasing in their corresponding conjugate base, and that's why their acidic character will decrease. So this is all about the compound with oxygen. Next we'll talk about their compounds with. Third is reaction with halogens. Well, as far halogens are concerned, they react with themselves to form large number of compounds known as interhalogen compounds. So here we'll see interhalogen compounds. I'll give you one example of that, like iodine heptafluoride, BRF3, or ICl5. These all are interhalogen compounds. The interhalogen compounds are found to be more reactive than halogens, because in interhalogen compounds, suppose I want to do fluorination somewhere, and if I'm using fluorine, one molecule of fluorine will give me 2 fluorine atoms, whereas instead of that, if I use one molecule of IF7, I'll get 7 fluorine atoms. So fluorination will become easier. Moreover, the bond dissociation enthalpy in interhalogen compounds is lesser as compared to halogens. That's why it becomes easier to break these bonds, and that's why interhalogen compounds are more reactive than halogens. So as far this class is concerned, in this class I've just told you the basic trend and the basic reactivity, like with oxygen, with hydrogen, with halogens. I'll in the next class, what you'll be doing means I'll show you some of the PPTs, and in those PPTs we'll have some chemical reactions that I'll keep on, means I'll explain them to you. I'll not write them, I'll just explain them to you. They are already written in the PPT. If you want to write them down, you simply write them down. Just mug them up, because these reactions, they are very important from the exam point of view. Many a time these reactions, they are given, you will be given the reactant part and you will be asked to complete it. Generally, when we talk about the 3 marker or the 5 marker question, it's not like one question, the weightage of one question is 5 marks or 3 marks. Generally, it have parts. The 5 marker or the 3 marker question is divided into 3 part or 5 part. And in those part you have been given, generally you are given the reactants and you have to write down the products. So in the next class, we'll be revising this chapter from the PPTs. This is what I have taught you today, and in the next class, we'll be doing whole of this chapter from the PPTs. But before that, I would like to request you one thing, that please do subscribe my channel and press that bell icon so that you can get all the notifications. So that whenever I'll upload the next part of this chapter, you'll get a notification for that. So this is all what we are going to do in this session. Thank you very much.